Yeah, me and Michael.
Michael's
here, yeah.
We both bet on who only would show up, and we both brought.
Yeah, we thought Rebecca would make it.
Yeah, she's good at coming.
Oh, well, that's not smart.
Sorry, I thought Andrew was going next.
No,
you don't know.
You just update.
I thought Andrew was
Well,
going
he
next.
has to go.
Oh,
Yeah, that's right. Has to go soon.
I've already explained half. Okay.
Well,
Maybe to take
it's just
over.
gonna be a cliffhanger.
It's
Alright,
It's
ready?
cool.
How is this being
I'm ready.
recorded?
Yeah.
I didn't do my hair this morning. So, this is WRF, the Weather Research and Forecasting Model. So, what is WRF? So, it's the Advanced Next Generation Mesoscale Numerical Weather Prediction and Simulation. It's a bit of a mouthful, but basically it's a very advanced engine for simulating large-scale weather systems up to pretty much the scale of the entire planet. It can run pretty much the entire planet's weather systems all at once. It's made up of two primary systems, the data simulation, which is the WRF pre-processing system. So you take your atmospheric measurements and initial conditions and you plug it in and it sort of churns away and maps it to your domain where you'd like to simulate. So for instance, if you wanted to have a look at where the cyclone that you think is developing is going to make land, then you'd set up your domain system over the area of interest, because obviously it's, simulating the entire world's weather is quite computationally expensive and unnecessary if you're only really interested in one region. Yeah, so the other part is the highly parallel weather engine, which is extremely scalable. You can pretty much scales fairly perfectly with as many cores as you can throw at it, really, because it just breaks it up into smaller pieces, and they only communicate every so often. So most of the time is really spent just on really computing itself. So there isn't too much communication really. So it was started by NCAR in the United States in the 90s when the computational power of high-performance computing was starting to approach the point where people were saying, well, you know, we could probably start actually simulating weather with this, and you know, maybe make the weatherman's predictions a bit more accurate. So not only is it just used for real-world simulations, it's also used for simulating ideal cases and stuff like that. So you may want to investigate how your new model for, say, precipitation works on this cyclone system, like not necessarily a real cyclone, but just one you've made up. So why you should care? Well, you have to, because it's part of the competition, so there's that. Also, better weather forecasting for natural disasters with things like hurricanes will lead to better forecasts of where the cyclone will land, the extent of its damage, and can help improve evacuations and stuff like that. It also, a lot of people always complain about how inaccurate the weather predictions are, and so understanding the way weather systems evolve with time is important for not just scientific exercises, but also for the general public as well. So if we get into the technical details of WRF. So as you can see here, we have the your WRF pre-processing system, which I talked about, and you have other analysis and forecasts and observations, because machines aren't very smart in the sense, well, they do exactly what you tell you. So sometimes human intuition is also required to achieve a perhaps more plausible model. So it's plugged into your digital filter, which filters the data and all that sort of stuff. Then you see it has your two different dynamical solvers, which Ilyas will talk about in a bit more depth, the IRW and the NMM. And as you can see, it sort of does that, and then you get your result. So a little bit more on the WRF pre-processing system. So it's made up of three main parts. You have your static data, which is essentially like geological data, so mountains, heights, elevation, soil densities, all that sort of stuff. Stuff that basically doesn't really change in the sort of timescales that we're dealing with. Then you have your grid data, which is your initial atmospheric conditions, so things like temperature, pressure, water, humidity, all that sort of stuff. So GeoGrid takes your static geographical data and maps it onto your simulation domain, so where you're interested in simulating. Similarly, the grid data takes, because you can essentially get, there's multiple different formats in which atmospheric data comes from. Everyone has their own real standards. So ungrid is the intermediate step in between taking all the different formats of data and turning it into a format that WPS and WRF will understand. MetGrid then combines your static GeoGrid data and your atmospheric data from ungrid into just one big file, and then it passes it to WRF, which then runs the simulation. You can also have nested domains in WRF, because say you wanted to simulate the weather for the United States, so you'd have a large, perhaps low resolution model for the whole United States. If you were interested then specifically in a particular cyclone approaching, you would nest higher resolution domains inside of the larger domain, and so you'd get more accurate and more detailed weather simulation results, as you can see here. They can have different time step levels, so you may have the large one every 6 hours, 3 hours, 2 hours, every hour, that sort of thing. There are certain restrictions, as you can see. You can't have domains that intersect without being contained within one another, if that makes sense. Like they have to be sub or either entirely disconnected, having overlapping but not, what would be the word, hierarchical?
Subsets?
Subsets, yeah, isn't allowed. For obvious reasons, if you think about it, like how you really simulate cross intersecting weather systems like that. So that's all the slides we got today. So we're hoping to do a bit of a technical demonstration of the WRF system.
Yeah,
But first, Ilyas will go over the mathematical models a bit more.
hopefully. What's that?
Have you got VGA?
Yep.
Cool.
Alright, so I'm basically just going to cover the two main solvers that are used in WRF. That's just the intro. So the two different types of cores that they use is the Advanced Research WRF and the NMM, which is the non-hydrostatic mesoscale model. Most worldwide companies use ARW. I know NCAR uses it. It's actually a bit more of a there's more support for it, and it gives you a bit more information. That's usually what you want in this kind of a simulation. So NMM, the main difference between the two is firstly the way they calculate the equation used, the underlying mathematics used for the calculation. So in MMM you have the advective form, which is that just basically fluid and the way the molecules and fluids move in the simulation. And if I just show you the comparison, ARW is flux, so it's more like your wind speeds, your velocities that maybe you want more of. Differences also in prediction variables, so NMM uses velocity, temperature, pressure, and column mass. So this is all the stuff that NMM can predict for you. ARW uses momentum, entropy, geopotential, and they both use column mass, as you expect. One of the biggest differences as well is the Arakawa grid used. So Arakawa grid is basically this guy, obviously Arakawa, came up with this concept of using the grid system to predict stuff. So basically, NMM uses actually the latest version of the grid, but again, it might be the latest, it might be more accurate, but it might not be what you actually want for your prediction, for weather. So this is the A grid. So this is the theta is your static thermodynamic variable, so it's your temperature, your pressure, entropy, whatever. U is your wind speed velocity in the x direction. So if you think about looking at flat on the ground, U is your x direction, and V is your y direction. So the circles represent where the calculation is being made at. So if you can imagine the circles being at every center point of a grid. So this is obviously a 3x3 grid, with the circles being at the center of each square. So
2x2 grid.
2, it's 3x3.
I thought you said
Oh,
they're at the center of the square.
Yeah.
You imagine
Like a grid
the
going.
imaginary lines.
Yeah.
Oh,
Yeah,
okay.
so
I thought they were the intersections.
No. Okay, so
Kind of like tic-tac-toe.
yeah, exactly. So the A grid was a very old grid. It's very inaccurate now because everything's measured at the center points. You don't really have any knowledge of what's happening around you, really. It's all dependent on your resolution that you're using. This is the actual C grid used by ARW. So what happens is the thetas are now moved, so your static variables are still in the middle, but in between, so if you imagine, like, this is the grid, the intersects in between, so this is your grid line, so the intersects between each square is now being used to calculate your wind speeds, which actually gives you a better understanding, because now, if you were looking, let's say this is the eye of the hurricane that we're assessing, You get all the thermodynamic happenings inside, but you can get the wind speed around it, which is actually what you want rather than wind speed at specific points. So that is C grid used by ARW. And then there's E grid, which is actually kind of complicated, but it's used by NMM. So what happens is that it actually picks up your wind speed variables. So T and Q in the sense are theta. It's your static thermodynamic variables. And what happens is it lifts off, it staggers it in a way that it rotates and staggers, so that it gives you, so that you're allowed to view all your variables onto one plane rather than having sort of like things stacked up. So in this one, it's sort of actually just stacked on top of each other. You're not actually combining them, so when you look at the data, it's kind of like, you kind of can only view one thing at a time rather sort of thing. Whereas in the E-grid, it sort of combines it. Also, in E-grid, you can see that all the data points are actually now just a half grid, 1.5 grid away. Yeah, it's kind of complicated, which is why I thankfully found this little image, but it is a bit of a, yeah. Does anybody really get that? I find it a little bit hard to explain.
I just don't understand why does it matter, like what's the point?
Oh, it's just the accuracy, like different kind of accuracy.
Yeah, and this is used by the NNM computational engine,
Yeah.
and so they fundamentally operate on different equations. I've got the PDF
So you've
here.
got,
This
so what's
drives
TQ
into the
represented?
TQ is your theta, so it's your
Yeah.
thermodynamic stuff,
Yeah.
so like entropy, pressure.
And now you've got the wind adjacent to it, or directly around it, right?
Yeah, yes, kind of thing.
Okay.
It's just the way that the way that NMM uses like a different set of equations to calculate stuff compared to ARW.
But aren't U and V dependent on where your buoys or where your weather stations are?
U and V are your wind speed, right?
Yeah,
But
so
they need to measure that somewhere, right? So
No,
No,
the wind speed is calculated off pressure differentials and stuff like that based on your atmospheric data.
They're not
your
measured
initial conditions. They're,
explicitly.
they're generated by the computational engine, not as
Measured.
not measured.
Values.
Because if
Oh.
you imagine how many weather stations you need to be able to have data points everywhere, so
Okay.
you really just use like satellites to perform scans of like
oh,
pressure.
so this is how they're displaying it, like each of them's kind of like a pixel.
Yeah,
Okay.
yeah. That's a good analogy. Yeah, that's the resolution of the model.
I get you. Alright, cool.
It's actually a pretty smart way of doing it.
Yeah. Cool. I think Dylan's going to tell you more about GeoGrid, but does anybody have any sort of questions? I know there's probably a lot of questions about the tables, about the grids, but anything I can...
had one question.
Yeah.
On like the third slide, there's a guy saying something, but I didn't have time to read it all.
Third slide.
I think it was a joke.
Oh,
I think-
on my one.
No, I'm actually serious. I want to know what he said.
Oh, okay.
Was it a
Oh,
joke?
Was it
yeah,
a-
it was a joke.
It
It was
was
a
a
joke.
joke.
Star Trek
It's
joke.
a reference to Star
It's
Trek.
a-
We could.
It says, I've got it. We could remodulate the deflector emitters to inverse the polarity of our shield matrix. That might invert the effect of the force beam. It was just
That
Joey
makes
hasn't
no
getting
sense
technical.
whatsoever. That would,
Okay,
make,
fair
that would
enough.
make you take more damage. That's just silly.
I think Dylan wants to
Funny
talk
thing about Star
about
Trek was it made sense.
the actual
yeah. I was just gonna run
preprocess
through
now.
a tech
Yeah,
demo.
the preprocesses.
Polarity.
Can you use your one? Just because I on my keyboard, so
I don't know if you can use this one for the...
have you got Modi X down?
Yeah.
Yeah, that'll work fine.
Hopefully it works out fine. I don't know if it's going to work fine. I did change some stuff in it.
Why don't you let Dylan log in then?
Yeah, you can log into yours.
Cool. Why is it automatically logging you in?
No, that's just my piece.
Okay, new settings. Cool. Dum, dum.
Are you on Epic or Fauna?
Yeah.
Wait,
You just type it in there.
You sure?
Yeah, you got
SSH.
SSH.
Well, not...
Yeah, SSH.
Yeah.
SSH.
No, that's my computer.
Oh, this is actually running on your computer.
yeah.
Yeah, sorry. Nope, that's
That's not...
sorry. That's the UGP server. Do we need to specify what's forwarding? Does this one do it automatically?
It should
Are you
do
sure. And just do
or
it anyway?
dash Y or
Dash Y
No, it
ignores.
does it automatically. Don't do dash X.
Why not?
Oh, I think it might. Okay.
Is an excellent thing.
Yeah.
Why has some authentication issues or something? I was told not to use Y. But,
okay.
Let's do the
so let's.
Nice.
There we
Should do that.
go. Okay.
Is this like a set for executable even?
Yeah.
It's just gonna
Just
be
do something
like
that interactive drill.
for 5 minutes for the next set.
I didn't have too much trouble starting the job earlier.
Yeah, I see. It's just some computers like my
It
laptop.
shouldn't take that long.
my laptop takes forever,
Yeah.
and then hopped on Rebecca's and did it instantly.
It was a
I don't know what it is.
Rebecca.
And then I was but then I was at ECU. Then I was at ECU like half an hour earlier, and I got interactive jobs like that. It's just this. I think it's just this laptop gets bad Wi-Fi or
An
something.
interactive job I compared earlier.
Oh, really? But there was like 10 seconds between that and that computer, and it did it instantly.
Well, have you got one logged in on yours, or did I log it out?
You just log it out.
My bad.
Oh no.
It'll be fine. It'll only take them like
In the
a minute.
meantime,
Show us a YouTube
have that
video or
PDF.
something. Keep us entertained.
Yeah, show us some text.
Oh, is it?
Yeah,
Yeah, the one that was like a breakdown of the
Rebecca.
equations.
Yeah.
Where would I find that
No
Linux?
cat.
I can't find the Linux directory. Where would that be?
Would you want to just show them the
Paper now.
It
Vega
would
now?
be
Yeah,
in
while we're waiting for it.
the Slepsy directory somewhere.
Alright. So in the meantime, while that's working, let's do Vapor.
So this is one way of visualizing the output of
Oh, nice.
Do you wanna?
yeah,
You're gonna have to put this.
you're better at it, so you do it that.
One of those
Alright,
little
so we need space now.
Those are counties.
I'm gonna apologize in advance for the.
Kinda
It's
like
hard to
shires.
navigate Vapor. It's
Wow,
kind
that's
of
a lot of-
counterintuitive, so
Wow.
I'm gonna try and make it work fine. Cool. Alright, so the first thing you have to do in Vapor, which is the visualization tool that I'm now using, is that you can obtain an actual world map from the NASA website, which is also in Vapor, so it automatically assigns you a region that you specify with longitude and latitude, and you can put in the different cities and countries, like within states, so obviously you can see the breakdown there. Okay, so the first thing we're going to do is, is that it's looking a bit flat, so what you can do is you can adjust the visualizer settings to give you more of a 3D look, because our data is in 3D. So, and I'll add a timestamp. Nope, not that one. Timestamp. So now we should have a slightly better one. Okay, so from here we place our data in. So this is our data. It's a little bit boring, but it'll do for now. And, oh, that's weird. Doesn't like this.
Just, yeah, it'll go away when you
Okay, so what we want to first do is fit the data. Make sure it's okay. I'm actually going to put a transfer function that makes it look, allows you to see it a bit better. Okay, fit to view histo and fit data. Okay, so if I move this slightly forward in time, you should begin to see a little spiral develop. That is obviously Hurricane Katrina coming into New Orleans. So let's start it again. Okay, so what you can do is that you can actually adjust the different opacity. So if you want to break it down closer. So as you see, if I make it really low, at this point in time there's not much of wind speed, not much of turbulence really, so it's pretty bare. But as you go further on, you should see a little tornado. I mean, we were supposed to have 58 steps in this, but there's only 12 steps because it's a massive, massive, massive file. So forgive us for this.
ran out of space.
Can
Yeah,
you
I'm not-
rotate?
Sorry?
Can you rotate on an angle?
Yeah, you
So
can
you
rotate
see
it.
it on the side?
Yeah.
Okay.
But what I want to show you guys is the
The ISO or the probe?
I'm going to show them the region first. So
Oh, yeah.
basically, you can cut, let's say you want to analyze inside the eye, so you can actually cut it in half.
Oh, nice.
And so you can actually see, and then you can actually lift it up as well. So if you want to look underneath for some reason, you can actually see. I'm picking better looking part. I wish there was a better part. But, like I said, there's not much in this one. But, yeah. Okay, so that's your, obviously the color shows the, actually, I know what I did wrong. I'm going to, forgot to use, so basically, Python lets you actually set a variable type. You can create your own variables within Vapor using Python. Here we've used one in the process. This is UVW. So this is the square root of the squares of the different components in the x, y, and z direction of your wind speed.
Yeah, because just before he was only visualizing X.
Yeah. So that's why it was
that's why it looked a bit weird.
Oh,
But
okay.
now this is actually everything together. So it actually should look a lot more vortexy. Yeah.
Oh, yeah.
Yeah, so this is the actual wind speed magnitude.
Yeah.
Then before we were just only visualizing the X component of that. Yeah, that looks a bit more like what we have.
Yeah.
Hey.
And so if I brought this up, oops. So yeah. So make that less opaque. And so you can actually see the structure of your little hurricane. So what I want to do now is actually show you the actual flow. So in flow you can actually show the actual directions of your turbulence.
It's like arrows pointing.
Yeah. So that's your direction of your turbulence. I'll make it a bit nicer by making that smaller. Making the seeds. Where's my seeds? Oops, wait, that's not meant to go. It's directional. Wait, where's my seeds? Seed count. So I'm gonna make that 50. So you can sort of see it better. And I'll make that a bit smoother. So these are all the turbulent airflows around the hurricane. And if I remove this, if I remove that overlying data and keep just the flow, oops, and if I'm, yeah, it's like a giant spaghetti monster. So you can actually see the different airflow. I really need to work on this thing. You can see the change in airflow as it moves.
Wow.
Cool.
Nice.
And you can actually specify the direction of the airflow using arrows. So if I use arrows, yeah. The reason why the arrows are so stacked is because I put the smoothness at 20, so it's calculating every small step, rather than if I just made it like, if I made it 20, there's going to be less arrows, but it won't be as accurate, obviously. It won't be as smooth. The line's going to be jagged as hell.
Do you want to show the isosurface as well?
Yeah.
What if you change the flow length? What is that?
Flow length, that's just like how long the thing is going to be. So, yeah.
Okay. Oh, okay.
It's just the length of how long you want it to like extrapolate out into.
Yeah.
So, I'm going to get rid of this for a second. Right, so the next one is the ISO. So this, as Dylan will explain,
Hey, creates a mesh.
is, yeah, wait, let me just adjust the variable.
Yeah, it's a bit.
Yeah.
Can
Let me
you
fit it
maybe
for you.
drag it? I think it's more interesting around here.
Yeah, yeah,
Just
I'm
gonna
gonna-
have to find.
Let me just bring back to 1 actually. Yeah.
Drag it out, and just go at the top. I think you made the vortex. I think is more visible around here, if I remember.
A bit more up there.
Just try it.
I think
back this up.
I'm gonna go forward in time a bit more. Let me just remove the boxes. It clips a bit, but it's doable. I'm trying to find the. Wait, do we fit the histo in?
You just gotta drag it around until you get like your most amount of detail, I guess. So an isosurface is essentially much like a barometric line or an isoline you'd find on a weather chart. It's essentially all the points in 3D space that match a given wind speed velocity, which is like you can see on this histogram. And so then it forms a surface based off that. So it reveals some of the structure
I
of
think
the.
we can get it like if we get it right around here and we move forward.
Yeah, you can kind of see into it. We had it really cool last time.
Yeah.
But you can see like the central air column here and stuff like that. So if you maybe if you get the can you put the probes back? Because that would allow you to visualize it in terms of the actual motion of the.
Might as well explain about the probes as well then. So what we're doing here
Where's
is
it
wait.
Oh, wait, do you mean no? I meant the flow. Sorry, not the probe.
Okay. The flow.
Or is the isosurface kind of like
Yeah, it's gonna eats up.
okay? Someone's got some rendering glitches.
Yeah.
Can you change the render order so the
I'm not sure.
okay that's not working well.
That's not working at all. Maybe if I reduce the number of.
What if you
No.
disable the ISO?
The ISO's being drawn in
then
front
re-enable
of.
it.
Yeah.
Just
Just
disable
Maybe
the
I-
ISO
yeah,
and
then
then
re-enable
re-enable it. No?
There you
No,
go.
there's no Z buffer by the way.
No, it's no Z buffer.
Okay.
That seems odd. But yeah,
So you can sort of see
just turn off the
the flow. Yeah, flow's a bit crazy.
All right, but basically you can see the structure of the
Yeah, you can sort of
cyclone
see it
bit
there.
based off the wind speed velocity, and so you can see the central column of air around the eye of the storm as well as the outer thing that's been drawn in, in addition to the inner vortex in the middle here that's being drawn down. So you can definitely sort of see a lot of the structure of the cyclone. I mean, I guess it's a little bit abstract. Actually, maybe if you got the total pressure for the normalized pressure.
Nah. Oh.
Yeah.
Pressureful. No, that's. This actually should be it, but it's not.
Okay, so go. Try temperature. Nope.
Anything interesting happening here?
Kind of.
Whoa.
Hydrostatic pressure, maybe? No.
No, it's
Again.
just in the layers. So, oh,
No, layers
it's
again.
always in layers. Which would make sense.
Rainfall. Nope.
No. The rest we've got is.
Yeah, it's the wind speed velocity
it's
then.
the-
Yeah, so as you can see, this allows you to visualize
Yeah.
the cyclone.
And the last thing we have for this one is that you can actually use a probe to actually cut the your hurricane vertically instead of just horizontally all the time. So what we do is that we put a plane in, like, fit it to the region. So this is if you were looking like at this level, if I cut the hurricane in half, this is what you're looking at.
Oh, okay.
So you can actually do it in the positive X direction.
Do you have a really low resolution there?
Yeah, because what happens was when we did this, we had the low resolution because that was the only one that would go into WARF without going over the data limit. So, but now we've done it in Scratch. I think Dylan has a copy of like the highest resolution one, but at this stage, yeah, we
Is
don't.
that like 10
No, you've got 11. You've got your
Is this the 10 one? This is still the 10M, isn't it?
yeah. So go up.
Wait, let me
Oh,
get it to
change it to the
UVW.
Yeah. But you can sort of see if you
cut it in
if you visualize this as a cross section through the vortex of the storm, that you can sort of inspect some of the
Can you
internal
like
kind of
move
like
it
funnel-like
forward or
structure.
back?
What
It
is
just
that in?
appears as though in the
Like
last
the
couple of
cutting plane, can you move it back?
Yeah. So the
it
cutting
seems
plane
like
you
your
can move it.
resolution just dropped all of a sudden. You have
I
better
can't move it
resolution
much, but
for
like if
that.
I cut it lower.
No, I think
So-
he means move the
yeah,
actual
I'm moving
plane.
it that way, yeah.
No, it's, I don't think it's manipulated
Oh,
through
no.
that box.
No, I don't think that box
It
is
must
on
be
there.
manipulated up further. Yeah, there you go. Isn't that it? Drag that around? Nope.
So,
Cross section view.
I think
it
it's something
makes
to do with
sense.
this one, the orientation of it, but maybe I can do this.
Center.
So you know what?
That makes sense.
Yeah,
there you
yeah.
go. That's what I was thinking.
So
Yeah.
if you just rotate it onto a better view and just drag it maybe through,
Um,
so you can get a
Yeah, because I was just interesting to see the.
Yeah. So obviously the difficult thing with this is you're projecting three-dimensional data, or really four-dimensional data, into 3D, and then that's projected from 2D
Yeah.
onto the screen, so you're always going to get information loss. And so the trick is essentially probing this information in a meaningful way that allows you to interpret basically what's going on. And so this has a number of tools to do that, as we saw, using the flow analysis, the isometric surfaces, and now the cross-sectional flow. Yeah, and so that will allow you to inspect the storms, because ultimately the data coming out of WARF isn't just academic, it's got real-world applications and real-world uses, and so being able to visualize that data in a meaningful way, especially to the general population, is very important. So this is just one way to do it in 3D. Often the one you see on your news broadcast is just the, I guess the top-down view of, say, the barometric pressure and rainfall and stuff like that, which you can extract using another program, or this one, but yeah. Did we have this interactive job started?
yeah. Oh yeah. Should probably check that. Yep.
Yeah. So we've already talked for a while, so I'll just try and quickly jump through this one. So where am I? Local projects. Actually, I was jumping into WPS. Okay, so when you're doing real-world data, you need the WARF preprocessing system. So we just go into data. Now, all of these files, and I think this is about 17 or 18 gigabytes worth, is static geological data, except for Katrina, which is our initial conditions for the atmospheric conditions. So as you can see here, like soil type data, land use, any number of different parameters which WARF requires in order to accurately simulate all the interactions between the geography and the weather systems. In Katrina itself, you just have AVMs, which are atmospheric variable data. You can visualize this if I just go, oops, rats. Open, and there we go, query. How do I scroll this? So we just trying to. This is basically the thing that opens up the. Opens up the file.
Did you predict that with your work simulation?
Yeah.
So I'm just going to tell us all the stuff that's contained within this these initial condition data. So as you can see here, it's all the atmospheric conditions basically. So you can see things like highest top freezing point, geological cloud water profiles, so the existing moisture in the atmosphere and all that sort of stuff, and we can inspect some of it. Display, and then paste. And where's control? Yep.
Shift, control shift.
Ah,
What?
Click the little mouse button.
click the middle mouse button.
No, that's what you last copy.
I didn't copy quit. What was the name of that variable again? They all have such weird names.
Yeah,
sorry,
it was
so,
like C something.
it's difficult to remember them. C. Okay. Copy. You reckon? Yeah, okay, there you go. Which should open up. Yeah, bam. Oops. What happened?
Like that.
Yeah, I broke it. As you saw briefly. Let's try that again. Yeah. So that is the ISO surfaces for water content in the atmosphere. And you can overload, you can kind of see, I think you can overlay the country data and stuff like that. So this is actually global atmospheric conditions at the time of Katrina. And then we take the simulation domain and only simulate, I guess, the area of interest. So that's your atmospheric data, which we then plug into WPS, and then it does all the fancy stuff. So we'll just put it out here. Sorry. Actually, I'm just going to go that. As you can see, these are all the idealized cases I was talking about before about a sort of trivial simulation of ideal systems. So they're all the different simulations that come prepackaged with, where you can program your own. Otherwise, there is the real directory, which is where you simulate your real. So these are the MEMs and stuff like that are symbolic links to your pre-processed data. Then you run WRF, and it sort of churns around for a little while. It takes a while, so I won't run it. But as you can see here, there's WRF out. Is some stuff we prepared earlier. So we'll just quickly load up a program to look at that. Now, this simulation I run was actually a nested simulation. So we've got the domain 1 and the domain 2. Now, domain 2 was nested inside domain 1 at a smaller region and a higher time resolution. So I think the domain 2 was every hour, and the domain 1 was only every 6 hours. So if we just quickly look at so you got 1D variables, 2D variables. We're really looking at a 4D variable because it varies with time. So as you can see here, your various things like rain, precipitation, and vapor. So if we have a look at the vapor, we can step through. You can see the basic sort of cyclonic structure.
Nice.
And there are other things like cloud. It seems like a lot less clouds than you'd expect, but for a cyclone. And things like rainfall. And if you want to have, I think there is a, here's one which shows you the nested domain. There's the landmass, which is basically, you can see the area in which we're looking at. Now, anyway, just then look at the domain 2. And so this is the high resolution nested domain inside that one. And if we look here, you can see that it's much closer to the eye of the storm, and there are far more time steps in here, 13 versus 5 in the other one.
And you got more resolution because you're closer, right?
Yes. So your the size. WRF, you set up a name list which sets up the things like the boundaries of the things in sort of in latitude, longitude, as well as your map projection types. I'm sure if you talk to any sort of geologist or anything like that, they'll tell you about all the thousands of different map projection standards and stuff like that. Yeah, and so this domain sits inside that one, and so it allows you to get your high resolution around the area of interest.
Can you make it like follow the storm or something?
I was actually just about to get on that. If you'll notice, the eye of this storm remains roughly at the center of the screen.
Yeah, I was just about to say that.
And so if we bring up the landmass, landmass, you see it's actually shifting.
Yeah.
And so WRF has this option called vortex following, and it'll attempt to identify the center of the storm and then adjust the domain accordingly to follow that storm. Because if you imagine if you're doing a long simulation of cyclone, it may cross hundreds of kilometers of area, and you don't want to be simulating that entire domain for the entire time. So WRF actually is capable of identifying the central vortex of the storm and then following and adjusting the simulated domain accordingly. Yeah, so there you go. That's WRF.
Yeah. Very similar to graphite.
Yeah, really good. How easy would it be to take the output of WRF when we're running it at the actual competition and output it into something like that and have visualizations?
Oh, it's pretty easy. The only problem we've had now is that Vapor's having an issue with shaders in OpenGL, and we're not exactly sure.
I thought you'd dump it to a file and then have an external computer because you wouldn't want to be taxing.
That's what I did.
Visualizing the data.
I essentially dumped it into the actual computer and then I ran it off my actual
Yeah, I think Vapor's running off this computer. But yeah, definitely.
I also noticed that a lot of it could be exported to like Blender or something else.
Yeah, definitely. There's actually another program called Mackay Voyager, which would allow set up automated scripts, and you'd have the general public interacting with the simulation, and it was a very high quality visualization. However, several months ago, the company has disappeared off the face of Earth, and I have the 64-bit Linux binary for the program, but I haven't been able to get it working, and so because the lack of the website existing anymore. But yeah, definitely, I think it would be awesome if we could get visualization up working.
Yeah, because WRF, basically what you can do with WRF is that instead of having to run Vapor constantly, you can actually save the sessions and then combine it into a movie file and then just loop that over and over
That's
again.
Right,
Yeah.
And we could just have it on a separate laptop.
With Internet Explorer. So if we go,
You need the non-existent.
I search ADEG,
Well, I like just go to it's easy.
you get a virus.
No, I didn't use it scan.
Okay.
I replaced that.
Yeah, so
Yeah,
Mackay Voyager
didn't have
gets
the
some
MDF
pretty,
file.
I mean,
Put
you guys
that
can
in.
kind of see that there.
Oh,
It's
wow.
pretty interesting. Theoretically, something like this would be able to be done with Vapor. We just need to spend more time exploring it and stuff like that. But yeah, basically anything that can really visualize volumetric data. And there's quite a few different programs out there for it. So it's a matter of finding the best one. But yeah, you can definitely have a display.
You can have a loop constantly, or if you want to loop different
right.
simulations at once.
Or if you really just go full visualization, you should find.
Because I've seen people putting data into game engines.
Yeah. You just have to. You can save. It saves each step, and you can just like link it
you
together.
just
with
play
file.
each step.
Yeah, there's Vapor. So there's another example of some Vapor where you can clearly see the cyclonic structure, while
That's
you've also got
pretty
your
awesome.
barometric
I guess if we had
cross-section.
if we had more time steps, I mean, we have like the first 13 hours in a very, very long, like 58-hour time step. Like, I'm sure somewhere around the 20th mark you get something interesting happening, but
Yeah, so yeah, you can definitely explore some interesting options for visualizing the output.
yeah.
There's the isosurface that we try to get working, and the flow structure. So you can definitely see the eye kind of structure you've got there. But yeah.
Awesome. All right. Well, thank you.
Any questions?
That's awesome.